There we go. Okay. What's up? Thank you. They're gonna qualify that. Adaptively so. Okay. I always forget those. Yeah. Chat. Out. Okay. Oh, the doggies are. Oh, we lovely. Yeah, should be. Place random coin tosses. Coin tosses. They're not real coin tosses. They're random samplings. Yes. Although this doesn't often happen in practice, they leave things out. They leave things the verifier has seen out in practice, and you can look up the trail of bits research. This is good. This is proof systems and other systems that use Fiat-Shamir, but they leave things out. They leave parts of the public transcript out. Yeah. Assuming everything that was recorded is actually the full transcript. It's just stupid bugs. Yep. Yep. Generate entire transcript. Yep. It's really, really nice if it works. Yep. Yes. Soundness. If you can prove it, it is true. Right? Whatever it proves is true. Yeah. Completeness can prove all true statements. Alright. Alright. I always have to look that up. I always forget exactly. I have like a vague notion. So, what does complex mean? Like, why do you care about complexity? Why can't it just be like good? It could be good and random, or indistinguishable from random, computationally indistinguishable from random within some parameter. Does it have to be complex? I don't know. Verifier's messages are unpredictable. Right. I'm clear on that topic. Remember the fact that they're chosen deterministically. Wait, has it been nearly 40 years and it hasn't been formalized? Okay. Come on. Boo. Sure. There. Yeah. Chat. Oh, that's in my front bed now. Let's go to the throat. Chat. Anybody in chat? Hello. Ooh. Hello, Levi. Argument transformers given by control on Stern. Show the fifth Fiat-Shamir transformers to grant a random model. Yeah. Caleb. Early works focused on applying Fiat-Shamir to constant. Oh. The always paradigms applied parameters to a super constant and more round the satisfy a strong round by round soundness. Interesting. This is proven in what you call it? Oh, what's the thing? What's the cryptographic thing? It's not the random Oracle model. It's not the standard model. It's not the standard model. It's the thing that Rand Kennedy always does. Oh, Michael Rosenberg would know. He did a whole bit to escape him. I think you're the right person. I must be. This is not proven in UC. I'll eat my hat. I shall go eat my hat. Okay, well, sure. It's nice to have that. A Fiat-Shamir hash function's model is entirely random function. The random model Verifier is secure, but since a random function is a financial description size, it is clear this model is purely an idealization. Okay. Exponential description size. I don't really understand what that means. One practice replace a random oracle with a concrete hash function. Argue that random oracles are true. Indicates a heuristic security of the construction that any attack can only be due to weakness in the hash function. Yeah. Netty Goldrake fundamentally challenges assertion by examining constructions because it was their secure and oracle model will become totally insecure when random oracle is instantiated, no matter which concrete hash function is used. What? Oh. It's gonna break my brain. This is like 23 years old. Derek's a signature and any implementation of new law based on sensory scheme. Okay. Coalescer and collide specifically gives them a secure interactive proofs with Fiat-Shamir transfer results in a secure, insecure, non-interactive protocol again. So what the fuck have we been doing? Okay, extremely contrived protocols that were specifically designed to fail. Thus, it was commonly used such as and output pro practice. Closest tons of more practical works even made Batriska will show that the standard approach for constructing hash-based proofs becomes insecure when applying FSR. Still, even the result of the polynomial is one online components in the system and indestructible proof for polynomial commitments contract. While as most totally these protocols for applying distribution servers and secure these attacks based on unnatural components of known chess and alternates. Prove the plausible protocols are not intentionally designed to be susceptible to such an attack. Okay, fine. In this work, we exhibit an attack that breaks through much interior security of the standard, natural, and practical proof system. Similarly, prior works attacking it, no matter what Fiat-Shamir hash functions using the following roughly stated sense. For every choice of Fiat-Shamir hash function, there is a natural instantiation of the proof system for which we can prove a false statement. Please define all those words you just used. Oh, I think I picked a long time to do this. Never got the ZK stuff. It's a half skip and a jump away from signature scheme, sort of. You're just proving different things with different kind of leaks. Tech does not point out a weakness in particular hash function. It shows that some natural schemes are insecure in a strong sense. For the reason series does this security jump paradigm. I do not like this. I like Fiat-Shamir. We do not want it to be insecure. The direct profile for which another tag has been asked to stand as distinct argument proving correctness of a computation expressed by a non-deterministic bounded depth arithmetic circuit. Easy peasy lemon squeezy. Argument system based on a combination of multilinear and polynomial commitment scheme. Okay. Popular GKR protocol, Goldwasser, Kalai, and Rothblum. I'm not familiar, but okay. In the protocol, verifier is given as input the depth D, arithmetic circuit C, a public instance X, and a claimed output Y, and its goal is to verify there exists a witness such that C of X and witness equals Y. Yep. This proof system equals variance, considered a line of works. Has been considered in a line of works. And lies at the heart of practical deployed systems to expander. Not relevant, but okay. An MLP-CS allows the user to give short commitment to a large multilinear polynomial P, and later gives distinct proofs for evaluation queries of the form P of X equals Y. La 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 la. These variants differ at some implementation details and optimizations, but seem equally susceptible to our attack. Or, yeah. We've informed Polyhedra of our attack, and they've introduced mitigations. Cool. Driver stream for the win. Yeah! I have papers to read, so I'm doing it on stream. Okay, where's 5? Oh, I haven't gotten there yet. Let's see. Pointed out explicitly in these works, when compiled with Fiat-Shamir, the resulting protocol is secure in the random oracle model. Our attack shows that it's insecure when the random oracle is instantiated as long as the Fiat-Shamir hash function and PCS, you define PCS, are computable in roughly the same depth D supported by the proof system. Okay, so there is a constraint, not a proof circuit constraint, but a different kind of the colloquial constraint. More detailed interactive argument system combines MLPCS. Polynomial commitment scheme. They define it without defining it. Interactive argument system combines MLPCS commitment with the GKR protocol for depth-bound D. The protocol, which we denote by pi, comma D, operates as follows. Where's pre-processing? We love pre-processing. Parameterization, polynomial commitment scheme, sure. Key solves chosen in the verifier. Sure, everyone chooses parameters. Prover and verifier agree on the depth D of A depth D arithmetic circuit C. The verifier will use some short digest of the circuit, which we denote by bracket C. Okay, fine, sure. 5. Usually the short description is a hash of a suitable description of the circuit, often called a domain separated. Okay. Simply the code of an algorithm that prints the circuit description. The reason the verifier only keeps a digest of C is that we would like to draw in time sublinear the size of C in the online phase. Tech works for any fixed choice digest. Okay, fine. My mic is muted? Or am I just... See, did that fix this? Oh! It's not working. My mic should be working. Okay, good. All right. It might be... Sometimes I just go... It was not working at the very, very beginning of the stream because I switched computers and I had to turn it on. But, sorry. It should be working now. Okay. The online phase. Prover chooses an input X, witness W, and output Y. It sends X and Y to the verifier in the clear. Good. And uses MLPS-COM to commit to the multilinear extension MLE of the witness W. We denote the commitment by COM of W. 6. Multilinear extension is a particular way of encoding data. Okay. For the purposes of this work, the specifics of encoding are not so important, but briefly, for a finite field, multilinear function of a function f, little f, of series of bits of length m to the finite field is the unique multilinear polynomial f hat, where finite field elements of length m maps to finite field element that agrees f on bits length of m for additional d. Fuck it, fine. Some sort of encoding to the finite field. Sure, fine, all right. Verifier chooses a random point r, computes MLE of the claimed output y at the point r. Okay. Verifier sends r to the prover. I've done that before, Brendan. See my mic, sorry. Choose random. Wait a minute. Okay, yeah. Verifier chooses. Okay, yeah, and sends as a prover. Correct. Sure. All right. So sort of a challenge response thing. Okay. GKR used to reduce the claim about y to a claim about the MLE of the input X and the witness W. Yep. The verifier can check the claim about X by itself and uses the MLPCS to verify the claim about W. Okay. I really wish this worked with like an identity protocol. I understand that the best. Or we had a diagram. Have any diagrams? No. Of course there isn't. Why would one ever have a protocol diagram? That's just useful. Oh, okay. Input X should be thought of as parameterization of the circuit in practice is sometimes not required. Indeed, that will be the case in a basic attack below. See the section for more detailed description. Okay. Assuming security of underlying MLPCS commitment, the interactive protocol pi commitment D can indeed be shown to be sound. Which should be sound, but it's not. The non-interactive version is obtained by Fiat-Shamir by replacing the verifier's random coin tosses by evaluations of hash function H. For example, random value R, selected by the verifier at random in step 4, is replaced with a hash of the protocol transcript. R equals H of the bracket of the circuit, the commitment produced via the witness X and Y. Yes. How you do that, you just concatenate it all together. Doesn't include the parameterization. Like, maybe that's in the circuit. We denote the resulting protocol by Fiat-Shamir sub H of pi commitment sub depth D. Okay. basic attack. We show that the Fiat-Shamir H by commitment of D is not sound, aka we can prove something that's not true in the following strong sense. For every hash from MLPCS commitment, there exists a depth in the natural numbers such that Fiat-Shamir H blah, 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 blah is not sound. In our attack, we construct a circuit C prime, which does not need an additional input X and an output Y star, such that for every witness W, it holds that C star of the witness does not equal Y star, together with an accepting proof pi for the false claim, little pi, for the false claim that there actually does exist W, such that C prime of W equals Y star. Cool. Circuit C star that we construct in our attack depends on the choice of COM and H. In particular, if these involve some parameterization, such as assaults, or equivalently, they are families of functions that need to be instantiated, then these need to be known to the cheating prover in order to mount the attack. Okay. As such, the attack breaks the adaptive soundness of the scheme. Right. You have to know all this shit beforehand. You can't just try and tweak and tweak. eprint.iacr.org. That is where not literally all, but pretty much all the serious theoretical crypto papers get posted. There's like a sanity check bar. There's like editors that check that you're submitting, that anyone submits something is like, it looks like a crypto paper and smells like a crypto paper, but that includes like blockchain stuff, quantum key distribution stuff, and stuff like this. It's like going at the heart of like fundamental cryptography kind of constructions and assumptions. Yep, ePrint. There's, be warned, there's a ton of stuff. There's like more than 1,000 papers posted to ePrint every year now. It's like just kind of hockey stick. Okay, finite field COM is an MLPCS over the finite field computable by depth D COM, it's arithmetic circuit, and the hash function computable by depth D H arithmetic circuit. Then for every depth greater than or equals to D depth commitment plus depth H of the hash function plus order 1, okay, the FSH of the Fiat-Shamir transform via H of pi commitment of D protocol is not at 100%. Okay, fine. Circuit C star, which our adversary constructs to break soundness, may at first seem odd. Particular as alluded above, it internally invokes the Fiat-Shamir hash function H and the MLPCS commitment. Indeed, this follows inspired by the diagonalization-based approach. I would like a dash there. In the prior works. At second glance, however, we remark the circuits and both these underlying primitives are actually quite common in practice. I believe that. In particular, the context of recursive proof composition. Strad. If you and Sean and Dara haven't looked at this already, to look at it. No. Regardless of whether the attacking circuit C star. Thank you, 50th subscriber. Cheers and thank you. Regardless of whether the attack constructed C star is, then we construct is natural or not the attack. But there's replace that with respect to every circuit that is used. Whereas we exhibit a counterexample that demonstrates this is not the case. Persistence is supposed to guarantee sound. Yeah, okay. Hello, Mr. Adrian. Things become even worse when considering the following generalization of the attack and extension attacking circuit implementation. Ugh. Well, I hope to mitigate the basic attack by considering the function as unrelated to the yeah, unfortunately. We can extend 51! If so many subscribers, oh my god. Unfortunately, we can extend the attack to arbitrary circuits in the following sense, given a circuit C, which computes some arbitrary functionality. We can insert a backdoor into it, which allows us to prove any desired statement. Oh, I hate this so much. Any input X star and a desired output Y star, we can modify C into a new functionally equivalent circuit C star. A C star computes the exact same function C. And yet we are able to produce a proof of the statement exists a witness such that C star of X star and witness equals Y star. whether or not the statement is actually true. The only minor restriction we impose is that the witness size for the circuit be at least as large as the digest bracket C of the circuit. See? Right? Something cool. We refer to such circuits as admissible. Okay. Extend the attack. Let F be finite field. Commitment and LBCS over C computable at depth G. Blah, 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 blah. Same shit. There exists a polynomial time algorithm given as input 1 instantiations of the commitment of hash 2 depth P admissible arithmetic circuit T, and 3 desired input X star in the finite field of extension of the finite field, and output Y star in finite field L. The fuck is L? I think we all know what it is. They didn't define L. The fuck is L? Did I miss L? I think I did. It's just size. No. Oh, size. The algorithm outputs circuit C star to D prime equals D plus D commitment, just order of D of H times the log of L, and a proof pi, little pi, such that C star computes the exact same function as C, Fiat-Shamir transform using H, whenever it accepts. Oh yeah. Except given C star, X star, Y star, and pi. For Theorem 2 demonstrates the crucial point. The soundness of the Fiat-Shamir transform for big prime of the commitment and D, and potentially other protocols, fundamentally depends on the specific implementation of the circuit being proved, rather than merely its functionality. Given the difficulty of reverse engineering the implementation of the circuit, damn right, especially given tools such as obfuscation, one should take extreme care when using the proof system for any complex circuit C. This vaguely reminds me of just like allowing computation to be shoved into your thing, and it's just like fraud. Same with proof systems. Yep, Strad knows this in the bones. Yeah. Okay. Remark. There are sometimes these correctness very specific at circuits. Lookup arguments, in particular grand product arguments. I didn't know that there was such a thing as a grand product argument. You could just tell me that it's grand, and I believe you. Our tech does not seem to function as a canonical representation, which is extremely simple. Our tech does not seem to propose okay, because you can't do a weird hippity hop swap and do the different circuit, same implementation or same functionality. Okay. Theorem can actually be derived some correlative theorem 2, considering the circuit C that never outputs some fixed value Y star, since proof of theorem 1 is significantly simpler, we prefer to keep the representation separate. Right? Universal circuits. The response to violate the adaptive soundness of the protocol in the following sense. The cheating prover needs to know the full specification, the key and salt of the hash function polynomial commitment in order to construct and specify the attacking circuit. In 4, we give extensions to the attack. We utilize fixed circuits that are independent of the underlying cryptographic rules. In a nutshell, these are constructed using universal circuits and kinds. I don't know that. Alright, yep, the theory of perspective. The known counterexamples discussed above for the security of Fiat-Shamir major line way the theory later is attempt to establish the security of Fiat-Shamir transform based on so-called standard cryptographic assumptions. Is that about the standard? In order to do so, these works focus on compiling interactive proofs. What is that italicized? Or limited forms of arguments. Rothblum and Rothblum? Give the first proof concept based on strong obfuscation assumptions, but since then a line of work has constructed schemes that are secure assuming standard assumptions such as LWE or sub-exponential DDH. LWE, learning with errors, or sub-exponential decisional Diffie-Hellman. So far, this line of work is focused primarily on deterministic computation of sublimit determinism, specifically to get through Rick's barrier. Okay. Tech further motivates this line of work and raises the question of whether it can be made practical. Okay. It's interesting. They explicitly name check the barrier and they don't. Okay. Man? Weak Fiat-Shamir. Fiat-Shamir is easy to describe. In fact, these features. Yeah. I think they describe a barrier, and then someone reading their paper is like, you are also describing your own barrier. So now you get a barrier, and they get a barrier. Everyone gets a barrier. Yeah. But Fiat-Shamir describes somewhat notorious for suffering from implementation bugs. That's correct. Most notably, some implementations accidentally use a so-called weak variant, which is the computational statement being proved is not included as an input to the hash. Yes. Yes. All this shit. Is this the other one? Sure, why not? This is very, extremely, very related. Like, no, really, when you're like computing over the whole transcript, you need to include the whole transcript. This is led to an actual text, yeah. In this work, we consider the strong variant. Can be seen by the fact that the circuit description is included in the hash. Ensure that it's insecure when applied to the GKR-based argument system. Good, okay. Random oracle and uninstantiated Rocco Dotland. Dujmovic? Apologies. There's a natural, incompressible encryption scheme in the random oracle model, which becomes insecure when the random oracle is instantiated. Okay. Okay. All right, GKR. Doubly efficient, not doubly inefficient. Interactive proof for verifying the correctness of bounded depth computations. We describe the vanilla GKR protocol, deterministic. Ready to use crypto? No, I'm not. Deterministic computations with statistical soundness. And then section 2 discloses succinct argument. Computational soundness for non-deterministic computations. Okay. This suffices for attack being fairly unlabeled. Okay, vanilla GKR. Ugh! Time flies. Time flies when you're having fun with cryptography. The vanilla GKR protocol, the goal is to verify a claim of C of X equals Y, where C is a low depth arithmetic circuit over a finite field, X is an input and Y is a claimed output. Both X and Y are known to the verifier. Loosely speaking, protocol is based on the following steps. Output layer. First, the verifier evaluates multilinear extension of output Y at a random point. Yes. Sometimes the output is just a single bit, which case can be skipped in case India's original description GKR 15. However, a weak linear check to consider service longer output. Yep. And then the processing circuit layer is the core of the protocol's interactive reduction based on some check protocol. It reduces the claim of the multilinear extension of a layer I to a claim about the multilinear extension of a layer I plus 1, where the output is layer 0. Yes. Yes, that makes sense. The step is just running starting from the output layer until eventually we get the claim of the input layer. Cool. And then the input layer. Processing all the layers of the circuit, the verifier is left with a claim about the multilinear extension of the input, which can either compute by itself or is sometimes passed on to some other protocol. Yep, Norc5. Note that the structure of GKR means if a circuit form C of X equals C2 of C1 of X, the protocol we thought is concatenation of two GKR protocols. Yes. One distinct claim about the MLE of the output C2 to a claim about the input C for the circuit, and then viewing that string as the output of C2, and applying another GK protocol to resist later claim to a claim about the input X. Yep. Additionally, we note the location of the claims of the MLAs generate the interaction depending on the verifier parameters. Okay. For a detailed overview of GKR, see these papers when I'll apply perspectives to these other papers for a Theorem 1. Okay. GKR is a succinct argument, often used as computationally sound proof, aka argument for non-deterministic computations by combining with the cryptographic polynomial commitment scheme, COM. And this context goal is for given depth D arithmetic circuit C, which has n finite field elements by m finite field elements to output L finite field elements. That makes sense where L came from. This is where L is actually defined, but they just don't reference it until up above. It's a preprint. I wonder if they submitted it anywhere. They must have submitted it somewhere. When's the submission deadline for like Eurocrypt or crypto? I forget. Input X is a bit string of length n. Claimed output Y is finite field elements of size L. To verify that there exists a witness of finite field elements of length L, of size L. such that Y is the circuit computation of inputs X and witness W. The protocol denotes big pi commitment D proceeds through processing. Verifier chooses the parameterization column, and the prover chooses the circuit C, sends it to the verifier. Okay, verifier maintains a short digest of C, which we denote bracket C. In practice, it might be some hash of the circuit. Yes. Quote, domain separator. Yep. We love the domain separation. Commitment. Prover specifies an input X, bit string of length N, and output Y, bit string of length L, and witness W, a set of finite field elements of size M. Input and output sets of verify in the clear, whereas only a commitment alpha, which is a commitment of the witness to the witness, is sent. It's in the clear. Okay. Output claim. The verifier chooses random R, finite field element of size, or set of finite field elements of log L. Deduces a claim on Y hat of R. What the fuck? This happens verse 3 as in around my ransamus, but then I mentioned that. Yeah, me too. They mentioned that as like important and like in the like stream of work that kind of leads up to this, but I don't know. I haven't gotten there yet, and I'm less familiar with this kind of area. Okay, Y hat of R. Observe that since Y has length L, its multilinear extension is a function on log L variables. Okay. JKR. Prover and the verifier run the vanilla JKR protocol described above. Okay. To reduce the claim about Y hat of R to claims about X hat and Y hat. Did they ever define X hat and Y hat? I don't think they did. Fuck it. Whatever. Fuck it. The soundness of this interactive protocol follows immediately from the computational binding of the MLPCS and the statistical soundness of the GKI protocol. And of course, I don't think the computational binding is important of the polynomial commitment scheme, and yet they never define it. They talk about soundness a bit. Do they? Do they though? They talk about the polynomial commitment scheme. They don't talk about the binding, the computational binding of it. They talk about it's important. I don't know. I think this is one of those things that they're sort of like assuming it's sort of like obvious because like commitment scheme, but they don't actually talk. They don't explicitly say in their paper that like the binding properties of the commitment scheme, yada yada, like what the fuck they are, why they matter, but then they say because the binding properties of the commitment scheme and the soundness of the proof system, therefore blah blah blah. Yeah. But like this is an e-print, so hopefully they'll just. This is sort of nitpicking a paper, like, you know. Yeah, exactly. Anyway, yes. Computational binding of the blah 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 polynomial commitment scheme, statistical soundness of the actual protocol. Okay, now we throw some Fiat-Shamir at this fucking interactive protocol. The non-interactive variant of the protocol operates relative to Fiat-Shamir hash function H, in addition to the MLPCS commitment. Proceeds similarly to the above interactive protocol, except that the verifier's randomness is replaced by evaluations of the Fiat-Shamir hash function applied to the transcripts. Particular step 2 above, both parties set R to be H of the whatever, the domain separator hash, whatever, encoding of the circuit, the inputs X and Y, and alpha is the commitment to the witness. And the GKR protocol is run to check that the multilinear extension of circuit of X at the specific point R is equal to Y hat of R, where Y is the claimed output. The resulting protocol is just known as a FS sub H of big pi commitment of depth D. Okay, definition 6. Adaptive soundness of that. Let H be a hash function, commitment be a polynomial commitment scheme, and D be in the natural numbers. We say that this thing is adaptively sound if for every polynomial time algorithm A, there's given as input a specification of the hash function and the commitment scheme, and outputs a circuit C, input Y, output Y, and proof chi, the event that both, for all witnesses, it holds that the circuit with inputs X and W does not equal Y, and the verifier of the whole thing accepts, given the circuit X, Y, and pi happens with negligible probability. Basically, it's fucking secure. It's like the fact that you can make it compute to not match. Adaptive soundness being you can prove the true things. You can prove the things that are true. Completeness means you can prove everything that you can prove is true. It's kind of this backwards thing. But this doesn't really, fuck it. There's this adaptiveness. There's sort of soundness, and then there's like adaptive soundness, and there's sort of like an extra layer of interactiveness or kind of extra rounds of action. At least with like adaptive security in protocols that are like, for example, like MPC protocols or threshold protocols. There's like an adaptive soundness, which is like the adversary can fuck with different rounds that are happening, but like there's not a lot of rounds that are happening here, so whatever. Fuck it. Okay. Theorem 1 establishes that the whole thing is not adaptively sound, nor as we show in section 3 upcoming. The proof of Theorem 1 actually shows a highly efficient attack by means of verifier except a false statement. The probability 1. Okay. Breaking this fucker. H and commitment being MLTCS computable in depth D-com, but D equals DH plus D-com plus order 1, where order 1 is a fixed constant we determine below. For simplicity, we assume the H and com are computed by arithmetic circuits over the relevant field. Needless to say, no idea. Is there Boolean circuits that could still be emulated by arithmetic circuits? Sure, great. Okay. Proving a false statement. To demonstrate the attack, we construct an explicit depth D circuit C star and accepting proof for a false claim about the circuit. And it just tidy that up. The idea underlying the attack following blah is not to explicitly predict the verifier's randomness, but craft a proof or message, in this case a choice of circuit, for which the resulting verifier challenge will be favorable. Proceed to describe the attacking circuit. The attacker will be considering a circuit C star that only gets its input as witness, a witness in a set of finite field elements of size M, and does not get an input X beyond the witness. Does not get an input X beyond the witness. Interesting. We set M be sufficiently large so that the circuit digest bracket C can fit in the set of finite field elements of size M. Okay. Cool. For example, the digest is 256 bits long and the finite field is 128-bit field, then M greater than or equal to 2 suffices. Okay. For intuition on circuit construction, that we decide circuit C star and desired output Y star, these determine randomness R that will be used by the verifier step 3 and blah, blah, blah. Namely, R will be fixed to R equals hash function of the digest of C star, the circuit, Y star, the output, and alpha, the commitment to the witness, where alpha is commitment to some witness. Like for a circuit to be able to shamelessly predict R in order to mount an attack. The challenge, which is rooted in the notion of correlation intractability, is that there appears to be a circular dependency. It seems that whatever change we make in C star in order to predict R changes C star and therefore changes R, and we get back to square one. To get around the circular dependency, we simply provide C star with its own digest bracket C star as a witness. Own digest as a witness. Okay. Proceed the construction given the witness and the defining field elements of size M, the circuit C star of W outputs. What? Yeah. What the fuck is a kind? Kind? I don't even know what that is. Here. Oh. Computer program sees no input, produces a copy of its own source code as its only output. Why is that? He's a logician. Yeah. Coined by some dude in honor of philosopher such and such a kind. who made an extensive study of indirect self-reference. Yeah. Kind's paradox. Yields false sum when perceived by exclusion. Yields false sum when perceived. Alright. It's just a function that prints itself. Alright. Today I learned. I lost my place. Acknowledged injectability. Okay. Given the witness in FM circuit, C star of the witness outputs 2 field elements. Okay, that's specific. Plus the circuit C star of the witness is found as follows. Interpret W as circuit digest phi. Compute alpha as the commitment to phi. Okay. Compute gamma as hash of phi. Y star and alpha. For Y star is 0. Oh boy, output gamma and gamma minus 1. Note that C star is polynomial size and has depth. D commitment plus CH plus order 1 is required. Okay. Okay. Proving false statement, which construct an accepting proof string little pi for the claim that there exists a witness such that C star of the witness equals Y star, where Y star is 0, 0. This by construction of the 2 elements in the output of C star are always distinct. This claim is clearly false. Yeah. The cheating proof string is constructed essentially equivalently relative to the witness W, which is bracket C star. This feels like such a hack. Not hack in the bad way, but like, how? Yeah, okay. Where bracket C star denotes the digest of the above circuit. In other words, the proof is constructed as follows. Set the witness to be the digest of the circuit and alpha to be the commitment to the witness, which is the digest of the circuit. The remaining part of the proof is GKR transcript and normal PCS evaluation proof, which can be constructed honestly, as we explained below. Note this part by, is that tau? That looks like tau. The proof string is pi, which is alpha and tau. We consider the verification process of the attack. Recall the C star denotes the circuit. We set the witness to be the digest of the circuit and alpha to be the commitment to the witness. The real output Y of the circuit C star on input W. By construction, the circuit outputs Y equals gamma and gamma minus 1, where gamma is the hash of the witness, which is the digest of the circuit, Y star, and alpha. The multilinear extension Y hat of Y is simply the function Y hat of big X, which is little gamma minus X. What the fuck is X? Come on. Someone define X. Big X for me. By the construction of C star, we have gamma equals hash of the witness, Y star, and alpha, which equals the hash of the digest of the circuit, Y star, and alpha. Yeah, we know. By definition of the whole Fiat-Shamir transform of the fucking scheme. Formal indeterminate. Is that what X is? Is that really a thing? Big X. The R, the randomness equals hash of the digest of the circuit, Y star, and alpha. Yes. Thus, the evaluation of Y hat at the specific point R is equal to Y hat of R is gamma minus R equals 0. On the other hand, since Y star is 0, 0 is a multilinear evaluation at any point that's equal to 0. Include the multilinear extension of Y and Y star agree on the point R. This is such a fucking hack. This is great. The multilinear extension of Y and Y star agree on the challenge point R. From here on, the claim being proved by the GKR system is correct. In the language of round by round soundness, we've moved from a doomed state into accepting state. I need to go read that round by round soundness paper because that sounds cool. At least move from a doomed state into an accepting state. Brutal. And from here on, the prover can simply run the honest prover strategy relative to the honest correct claim that Y hat of R equals 0. Brutal. All right. This one cool trick for tricking Fiat-Shamir transforms of interactive protocols. Just instead of a witness, just hand it a circuit digest of the circuit. And some other shit. But like, oh. Okay, attacking. Yeah, I know. Well, it's great. It's like, oh fuck, why does this shouldn't work? Or I don't know. Why does this work?
but it does fucking work. It's like, attacking. Yeah. Attacking circuit implementation proof. Okay. Let the circuit be an admissible depth D arithmetic circuit for any X star in the space and Y star. We show how to construct a circuit C star that's fundamentally equivalent to C, for which we can prove the potentially false claim that there exists a witness such that C star of X star and Y and W T equals Y star. For the construction, it will be convenient for us to use a fixed arithmetic circuit if then else. Ugh. Okay, finite field 1 plus 1 plus L plus L, all right, into the space, finite field of size L. Such that for A of B in finite field and C of D in finite field space L, we define if then else of A, B, C, D equals A minus B times C minus T plus D, okay? Davis function is due to the fact that if A equals B, then if then else of A, B, C, D outputs C. And if A equals B plus 1, it outputs C. Okay, and we will be using this function for inputs such that A is in a set B or B plus 1. Okay. C as follows. Okay, construction 2. Circuit C as well as function G in which we realize circuit C star of X and W. Compute Y equals C of X and W. Compute gamma. G. Where the fuck is G? Some shit G. If W and Y is in the finite field, is now in the finite field using procedure described below. Compute U real of gamma minus 1, Y and Y star out if then also be real. Okay, fine, whatever. Oh, it's there. Okay, the function G of Y, witness and Y. Interpret W as a circuit digest. As a circuit digest phi. Compute alpha as the commitment to the circuit digest phi. Generate the claim about the multilinear extension of Y stars and GA protocol with the Fiat-Shamir and compute R equals hash of psi, not phi, psi. X star, Y star, and alpha, which is the commitment to psi. Let U fake be 0, 0, Y, and Y star, and observe that if then else of U fake is Y star. Simulate the GK protocol and the if then else circuit to reduce the claim about the MLE of Y multilinear extension of Y star at the point R to a claim about the multilinear extension of U fake at the point Y prime as follows. The prover follows the honest GK's prover strategy, blah, 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 blah. Okay, the verifier is going to use the Fiat-Shamir hash function using psi as the circuit digest. Okay, I'll put the first coordinate of R prime. Okay? Proceed to prove Theorem 2 is showing the C star is functionally equivalent to C. If soundness can be broken, could we prove something false? Equivalence of X, B, M, size of whatever, arrays, vectors, of size N, of elements in finite field being input, and the witness in finite field size M. Let X be circuit of X and witness be the real output of the circuit. And recall that we fix Y star as the desired output by construction to hold that C star of X and W equals if then else of gamma minus 1, Y and Y star, which equals Y. We note that the last inequality holds regardless of how gamma is generated. Thus, C star is functionally equivalent to C. Oh boy. Attacking C star. An attack proof claims to exist of witness such that C star of X star and W is equal to Y star. Proof is such attack. One steps G carry persistent argument. Prover is given the commitment and hash function H. Prover specifies circuit C star. Specified in the construction above, and the verifier stores the digest bracket C star. Prover sends X star as the input, Y star as the output, and alpha is the commitment to the witness, where witness is the digest of C star of the circuit as the witness commitment. Now the random part R and the multilinear extension of Y star is determined by the application of Fiat-Shamir hash of digest of C star, which is the witness, X star, Y star, and alpha is the commitment to the witness, which is a digest. At this point, the attack was illustrated in figure 1. Ooh, we have a figure. Prover and Fiat-Shamir verifier start engaging the actual GKR protocol to produce a claim about Y star hat of R to a claim about the input. It will be convenient to the circuit stars have on two phases. First phase concludes with step 3 in the description of C star. this vector, blah, blah, blah. Second phase, we apply if then else circuit to U real. Okay, good. Okay, come on. Prover starts emulating the protocol corresponding to the second phase of the circuit, i.e. the if then else computation. The prover, which we'll call the cheating prover, runs the honest prover strategy for the sub-circuit, but rather than doing with respect, just search and replace that to U real, it uses U fake, which is 0, 0, Y, and Y star. The verifier challenges, as usual, are computing Fiat-Shamir. Okay. Yeah. Yep. Sure. Okay. Let's claim that if then else of U fake is necessary is correct. The result of this step is correct claim about U fake hat. The claim of the form U fake hat of R prime is equal to V. Sure. The crucial point is that by construction of C star, and specifically the definition of G, it holds that the first coordinate of R prime is equal to gamma of G of the witness and Y. Using this, we establish the following simple claim. U fake hat of R prime is equal to U real hat of R prime. Proof. Since U fake and real differ only by their first two coordinates for every vector Z, it holds that U fake hat of Z minus U real hat of Z equal to gamma minus Z1, where Z is the first, Z1 is the first coordinate of Z to see what... Yeah. Claim now follows from the fact that the first coordinate of R prime is gamma. Okay. As we see, the claim dash derived U fake is true also for the correct evaluation U real. Thus, from here on, we could just run the honest prover for the correct T-carry computation and obtain an accepting proof. Okay. Wait, are we doing UC? Are we doing UC?
Are we?
Element?
No.
There's some UC floating around for some of these other papers. Yep. I'm not sure. Maybe it is. Maybe. All right. At this point, one might perilously assume that to deflect the attack is enough to ensure that G-carry circuit in question is like a team implication and instruction. So that I would probably encode like the like C, the bracket C encoding the digest of the circuit, and then like literally match on it as a witness. Like if your witness input matches the circuit encoding value, you reject. Like that's a real easy mitigation. That's not very nice cryptographic mitigation, but like that's a real easy like slap a vuln mitigation on your proof system. All right, as we showed. Yeah. Fuck. Yeah. The prover. It's all about the prover. The prover and the verifier see the circuit diagram. They have to be able to see the circuit diagram. So the prover at the very least will not spit out a proof that verifies if you try to give it a witness that well, if it's a malicious prover, I guess we're all fucked, right? Shit. Okay. Yeah. All right. Kind example. Yeah. Extremely. Oh, like, the fuck are you gonna do? You want a Turing complete virtual machine in zero knowledge? Let's get to the rest of the paper. Maybe we'll see if this is actually a thing or not. A realistic thing. Okay, a kind is a program that outputs its own code and it doesn't take any inputs, it just spits out itself. Turing complete language emits a kind according to the folklore annotation. Folklore. We should get Mr. Robert Eggers to do a cinematic adaptation of the folklore. Clean's second recursion algorithm. Okay, I thought that was Rogaway. No, it's Hartley Rogers. Okay, fine. I was like, how long has Rogaway been fucking cranking it out? Will it give me a PDF? No, it will not. Boo. Good place. Did I? No? Nice. Okay. Okay. We use a slightly simplified multi-layer notation for program P. We'll denote by P the partial computable function which corresponds to it. Partial because it returns ground if the program does not terminate. Okay. And bracket P, it's code. Okay. For any computable function f, there is an f kind, a program P that outputs f of bracket P. Okay. Furthermore, the size of bracket P is linear in the size of bracket F. Okay. For the proof from the sum, which is based on the proof of existence of kinds through the appendix. Okay. A rather curious example is a circuit that can be used to simulate a universal Turing machine. Figure 2. We do not describe it precisely, but list the properties we need. We note that the construction is not efficient. We will get efficiency back at the cost of some socialization. Okay. More importantly, the stack is independent of the commitment scheme in question. Universal Turing machine circuit T of N and M such that input W of size M, N. This encodes the initial state of the tape of the universal Turing machine, outputs the fixed size output of the Turing machine if it terminated in less than M steps. Special symbol ground otherwise. Normally, the output tape of the Turing machine can be large. We only output a fixed size chunk of greens. Okay, whatever. Theorem 8. There exists a family of circuits T prime of NM, such for any polynomial time commitment scheme in the hash methods. There exists M with M equals poly of M, such that the Fiat-Shamir GKR protocol for the circuit T prime of NM is unsound. We admit the dependence of series random lambda for clarity. Sure. Okay. Proof sketch. Consider a function f which computes and outputs the value gamma as described in the basic attack. So there exists an f kind P, yes. Series with Turing machine T of N and M. Random number should be appropriately large. Okay. Consider a minor modification T prime of T, which corresponds to T in terms of the results of the field element gamma and outputs gamma and gamma minus 1. We'll pass the code string bracket P as a witness to the circuit. This allows us to proceed with the same attack to construction where we present the output is 0, 0, with the fact there's no witness that yields 0, 0 output. Therefore, the circuit is non-adaptively unsound against any hash and commitment scheme with complexity bounded from above. Oof. QED. Motherfucker. Most trigger example in the section of sketch less universal is interesting. Okay. With G of N in N, O, N, and M. B. Universal GKR circuit with the following functionality. Starts with witness. B. Witness in, that means, where WC encodes GKR circuit with N in input size, M intermediate layers of N size M, and output layer size of size N out, and W in is a vector size N in. Outputs WC of W in. That can be improved, in my opinion. By appear this impossible amount to attack such a circuit. After all, the WC is incorporating the commitment. This is, of course, not the case. Commitment is the form F of commitment to WC, commitment to WN. The attack essentially reduces the original C star with commitment of WC playing the role of bracket C. Okay. Interesting for many commitment schemes is exactly the case. Informally stated, or 9 for any additively homomorphic commitment scheme, both truly additive such as elliptic curve-based commitments or weakly additive such as lattices. Heh. GKR protocol for universal GKR circuit M is unsound. Schemes additively homomorphic. Commitment W equals commitment WC plus commitment WN. By passing commitment WC is W reaches the original attack method. Yeah. Fuck. Fucking gross. Alright. That's annoying. While we are unable to directly mount this attack against Firebase schemes, it should be noted that many modern Firebase protocols use batching, which means the day passes commitment. W is in fact a disjoint union of multiple Markov words corresponding to different polynomials. Against such protocols, the attack can be mounted. This is so brutal. Oh gosh. I'm just gonna print this out and wave this at all the ZK people I know. Just be like, how you feeling, buddy? How you feeling? At least for additively homomorphic commitments, the concern is much larger. Specifically, to thwart the attack, the circuit designer must somehow ensure that there is no way of representing a commitment hashing computation, even a small, arbitrarily allocated part of the witness. Fuck. This completely restricts a feasible GK circuit as either circuits of bounded from above depth or circuits with extremely restricted data flow. Motherfucker. Fucking brutal. That's so brutal. Alright. Conclusion mitigations. Found the violation of Fiat-Shamir security of standard national protocol to be very concerning. First and foremost, it raises a question about the Fiat-Shamir security of other protocols. Damn right. This calls for significant cryptographic effort by the community in studying the security or potential insecurity of Fiat-Shamir of other protocols used in practice. Still, it is worthwhile to point out that some specific properties GK-based protocol that we consider this work, which will facilitate our attack. The concerned we didn't use circuit efficient hash function and a chance to it. Damn fucking right. What? We emphasize that we do not know attacks or protocols that don't satisfy these properties doesn't mean such attacks do not exist. Yeah, among other concerns, yeah. First, it's useful to compare the modern applications of Fiat-Shamir to those individually envisioned in the A's and I's, specifically the context of constructions of digital signatures. Yeah, I care the most about the signatures. Your MLDSA's ski sign is still Fiat-Shamir. I have to go back and look at UOV, you know, and Schnorr, of course. We have lots of Schnorr deployed. We love Schnorr. It's pretty. I'm curious about them. All these complicated interactive protocols and ZK things and proof systems. They're just a little bit more complicated. The hobbits, we love the hobbits. It feels dirty to do an impression of our dear leader. He's a very funny man, but it does feel dirty to do any impression of that guy. The original use was applied to very specific identification schemes built around concrete number theoretic. In contrast, modern usage is intentionally designed for protocols that are used to prove general purpose computations. Our attack leverages this in order to invoke the proof system relative to a computation that involves the computation of the Fiat-Shamir hash function itself, as well as polynomial commitment. Elaborating further on this point, the GK-based protocol, much as other protocols in the literature, has the key property of the prover does not commit to the full computation trace. Indeed, this is one of the most compelling features of the protocol. Okay? Fortunately, the fact that the computation is not committed also enables our attack. We can consider explicitly invoking the Fiat-Shamir hash function without needing to commit to the corresponding computation trace. Thus, a natural countermeasure for the GK-based protocol is to ensure that the circuit family considered is not powerful enough to compute the hash function. This can be due to any natural computational resource, but some natural ones are depth, as an arithmetic circuit, or potentially algebraic degree. All right. Maybe achieved by attempting to increase the depth of hash function used, possibly via composition, or reducing the depth of the circuit in question, possibly by committing to some of the intermediate values. If says that, well, we do not know exactly what pace of the countermeasure would be. Whether or not they actually secure is an important open question. Boom. Bit twiddling hash functions for the win. Boom. I don't know what that means. This is interesting. Let's see. This is very, very, very interesting. Let's see. When's the deadline? No. This may be submitted. I wonder. Maybe or not. Yeah, this is all like Ethereum and other people. Goddamn. Yeah. This is cool shit. It's very interesting. I do think that your signatures, your simple signatures that don't have all this extra shit in it are probably fine. But like everything else, every other proof system that has like a description of the computation and a witness, you're going to have to figure out just don't compute so much. Don't be so powerful. Because if you are, you're like, if your witness can be your circuit digest or whatever, like you might be fucked. You might have a dishonest prover or something like that, and you might be fucked. That's brutal. Cool. That's awesome. I'm glad I spent time on it. Cool. That's all I got. I have other papers in the queue about secure messaging, and there's probably some post-quantum shit somewhere. But thank you for joining me. More papers, more fun, more soon.
This is so brutal.
Signing off. Thanks for joining.
Bye.